This is appearing in a strange way on my screen, but it's fine up there. So anyway, this is work that I've been doing for several years, 4 or 5 years, with 2 collaborators, Humberto Llavador, who's in Barcelona at the University of Pompeu Fabra, and Joaquim Silvestre, who's at the University of California, Davis. And we have a number of papers, which this talk is based on, more technical papers. So Nicholas Stern, in his Stern report, I think began by saying that the biggest externality that the world has ever faced, that the human species has ever faced, is global warming. And I think that's probably correct. The evidence is overwhelming now that greenhouse gas emissions from industrialization account for the most rapid rise in atmospheric carbon that have been seen in hundreds of thousands of years. And if this continues, the main welfare effect will be a rise in global temperature, which then has implications for all kinds of things associated with water. Storms, drought, rising, diminishing coastal, rising sea levels at the coast, and so on. This is a graph, which a lot of people probably have seen before, of recorded temperature in ice core samples from Antarctica for the last 400,000 years. The rise in global temperature here is quite extreme, but this is not what's happening in the Earth. This is in these. I don't know why it's so high, 6 degrees, what that means, but the relative magnitude we can see. There have been oscillations in the past, and I think the so-called Little Ice Age is in here somewhere in the 16th century. But in the last 50 years, the curve has just shot up extremely rapidly. And that's the main evidence that what we're experiencing now is not a natural phenomenon, but it's due to, well, not, let's say it's due to man as a natural species, but it's due to man's activity, not other natural phenomena. Currently, the concentration of carbon dioxide equivalent, which means carbon dioxide and its cousin gases that also contain carbon, in the atmosphere is about 430 parts per million. If we stabilize at 500 parts per million, so there are 2 numbers one sees frequently. One sees this number, and one also sees the number 385 or 387. The 387 parts per million is just carbon dioxide. The 430 is carbon dioxide plus methane plus nitrous oxide and these other gases that are also greenhouse gases. So if we stabilize at 500 parts per million, then it's estimated that the 90% confidence interval for the rise in global temperature will be between 1.5 and 5.2 degrees Celsius above the pre-industrial level. I think we're now about a half a degree above the pre-industrial level. An increase of 5 degrees would probably eliminate 1/2 of the Earth's current species. Now, somebody pointed out at lunch there'd be other species that would evolve probably, but they wouldn't be the kinds of things that we're used to seeing. At present, concentration is increasing at about 1 to 2 parts per million per year, and so by mid-century we will be at about 500 parts per million if we continue with business as usual. Carbon concentration is a true public bad. That is to say, the actions of each affect all. And reducing the rate of greenhouse gas emissions requires international cooperation. The Intergovernmental Panel on Climate Change, the IPCC, was created by the United Nations about 15 years ago and has issued 4 reports, the latest one being 2007. And in that report, they propose levels of greenhouse gas emissions that would approximately stabilize concentration at 450 parts per million by 2050. I should say there are also scientists who claim that this is far too high. The most famous example of such a person is James Hansen, who's the head of the Goddard Space Institute in New York City. I don't know why it's a space institute, but anyway, his main work is on climate change, and he says we should try to stabilize at 350 parts per million, which means cutting back on the carbon that's already in the atmosphere. So this is the distribution of the gases that produce carbon. This is fossil fuel use, carbon dioxide. This is methane, CH4. A lot of this is produced by the rumination of cows, apparently. This is carbon dioxide produced by deforestation. That is to say, the fact that it's actually not farting. It comes out of their mouths, mainly, the cows. I just learned that. This is the CO2 that isn't absorbed by the forests that are cut down. So deforestation has a significant contribution to greenhouse gases. And this is nitrous oxide. The current emissions levels for a variety of countries are the following. This is just CO2, not CO2 equivalent. The United States is 19 tons per person per annum. This was a few years ago. 19 tons per person per annum. The world global level is 4.4 tons per capita. China is 4.62. But since their population is about four times as large as the U.S., they have now just recently overtaken the U.S. in total greenhouse gas emissions. So China is the #1 country now, the U.S. is #2. Russia is quite high because they produce a lot of petroleum. I put some of these this should be United Arab Emirates, not United Arab Republic, but I put some of these countries in to show you that because they have petroleum production, they have very, very high tons per capita and small populations. France is the most successful country in Europe, 6. Germany's 9. Because their electrification is nuclear. So nuclear energy is probably going to be in our future. India is quite low, but going up quickly. And I think it's on the next slide. Yeah, by 2050, the global population, so we're now producing, we have about 6 billion people, so we're producing about 24 tons. We're producing about 24 billion tons of carbon a year into the atmosphere. 6 billion tons, 4.4, 26 billion tons. And the estimate is that we have to get down to 18 billion tons by 2050. Since the global population is expected to be 9 billion, that means 2 tons per person by 2050. So the United States, if essentially all the large countries are going to have to cut back to 2 tons per person, the global average of 2 tons per person. And so the United States is going to have to cut back by about 90%. China only has to cut back by about 60%. So we have the toughest job in terms of reducing emissions. Nevertheless, it's not such a technologically difficult thing to do by all estimates we have and by looking at the history of technological development. It's it's far from impossible. It's in fact relatively easy from a technological point of view, according to most estimates, to do this. Please don't consult me and make me argue for that. I take that off the shelf. I'm not a physical scientist and I don't know the technology. But that's everything I've read says it's actually not so difficult to do. This is a graph which shows you how emissions per dollar have decreased over time. So it's a quite steady decrease of 1.7% per year of emissions per dollar of GNP. So this rate is going to be speeded up a good deal if we invest a lot in innovation for alternative energy production. It's actually not going to be impossible to get down to 2 tons per annum globally if we undertake the necessary investments. Now, the 2 major ethical issues and political issues, one might say, are, what's the fair way to share the scarce global commons between the present and future generations? And secondly, once we solve that problem, given the present generation's allotment, I mean, how much we get to shoot into the atmosphere, what's the equitable or politically feasible way to share the burden among countries at this date in this generation? And so I want to try to say quite a lot about the first question and a little bit about the second question in this talk. So to address the first question, my co-authors and I constructed a model, which is a fairly common type of model in what's called growth theory in economics, in which there's one household at every generation, a representative household, which stands for the average household. It will turn out it stands for the average household in the U.S., not in the world. I'll say why in a minute. So there's going to be one household per generation, and these generations go on forever. And the household consists of an adult and a child. The child is educated by the adult and becomes an adult with the child at the next date, the next generation. And this society goes on forever. And the question is, how can we organize production and consumption to optimize human welfare, something I'll be more precise about momentarily, and stabilize atmospheric carbon at 450 parts per million forever? Now, why is it going to be the U.S. representative household? Simply because the data that are available to us and that are reliable for parameterizing the model so we can actually make the computation are U.S. data. We'd love to do it with world data, but that would be a bigger job. We don't have reliable world data, and so on. So at this point, we've only done it for the U.S., but the results are still, I think, quite instructive. Now, what does human welfare consist in? So in this infinite sequence of households, one representative household for each generation, the adult is the producer and the consumer and experiences welfare as a consequence of the things that he or she produces and consumes. The child is simply a vessel to be educated, and then the child becomes an adult and experiences welfare of the next generation. Welfare consists in five inputs in this model. Consumption of a produced commodity. There's one produced commodity in the model, which you can think of as a universal consumption good. The second thing is education, which has value to the person, other than value to the person as an input into production, value to the person's welfare. Thirdly, there's the person's leisure time. Fourthly, there are two public goods which we put into the utility function of the consumer, of the adult. The first is the stock of human knowledge, the amount of human knowledge that exists. That's different from the person's own education. In other words, we say the quality of human lives is better if the society has more knowledge, both because it affects things like our life expectancy and quality of life in various ways, but also because we have a quest for knowledge. Human societies have always invested in art, in literature, in scientific research, and so on. That's the quest for knowledge. And finally, the quality of the biosphere enters into the utility function of the individual. We like to see species, we like to have forests, we like to be able to take hikes in the mountains, we like to breathe clean air, and so on. So those are the five inputs into human welfare. Commodities are produced by educated labor, by capital, and by knowledge. Production causes emissions of greenhouse gases which degrade biospheric quality. Children are educated by the adult, and the level of skill that the child eventually develops, or the level of education the child eventually acquires, is proportional to the teacher's level of skill and the amount of time that the adult spends in teaching. Okay? So it's time that the adult spends times the adult's own quality of education, level of education. Knowledge, like capital, depreciates over time but is augmented by workers producing knowledge. That is to say, part of the adult labor will be in the knowledge industry, doing research and development, writing poetry, and painting oil, still lives, production of knowledge. But knowledge depreciates, right? There's some knowledge from a generation ago which hasn't necessarily been forgotten, but is useless to us now, like how to make mechanical watches. So actually, economists estimate that the rate of depreciation of knowledge is quite high, higher than the rate of depreciation of capital. So here's a picture of most of the flows in this model. So what happens, we begin at a certain date, say the 5th generation, with a level of knowledge of the society, a stock of trained young adults who've been educated, a capital stock, and a certain quality of the biosphere. The quality of the biosphere goes directly into the welfare, or what we call the quality of life, of the adult at date T. Knowledge also goes directly into the quality of life. Capital is used to produce the commodity, and the commodity has two uses. One use is to go directly into consumption of the adult and to contribute to her quality of life, and the other is investment, which goes into augmenting the capital stock for the next generation. Trained young adults do three things with their labor. They do research in the knowledge industry, research and development, research, art, and science. They teach the youngster, and they work in the factory producing commodities. So in this model, since there's only one adult, she divides her labor among those three uses. Of course, this is a representation of the labor force of the whole society. And the fourth thing that happens with labor is leisure. So this green arrow, probably should have been a yellow arrow, goes, the stuff that's left over after working in those three industries is consumed as leisure and adds to the quality of life. Knowledge, actually knowledge goes into two places. There's an arrow missing. There should also be an arrow from knowledge into commodity production. Because as I said, knowledge is an input into commodity production. And that's how technological change is modeled. The more knowledge we have, that creates new technologies, which makes it easier to produce commodities. So that's a missing arrow. And I think I've done all the arrows now. Yes, education produces trained young adults at the next state. And so then at the next state, we end up with endowments of these four things again, just as in the previous state. So what we have in the model is we have a specification of what all these production functions are, namely the teaching production function, how we relate adult teaching to training of children, the knowledge production function, and the capital production function, how capital comes from investment and depreciation, and the commodity production function, how commodities are produced by knowledge, labor, and capital. And so the set of feasible paths is the following. I have to remember what's on the next slide. Oh, here it is. So a feasible path consists in the specification of all the stocks at the first date, that when we begin the model, which we take as year 2000, and then all the possible paths of stocks and flows that can be created ad infinitum from those initial stocks. So at each date we have many choices, right? How to allocate the labor, how to allocate the commodity produced between consumption and investment, and so on. So there are zillions of feasible paths. The problem is going to be to pick the best feasible path. And we want, in all the feasible paths, we restrict ourselves. Well, I think I'll come to that in the next slide, so I won't say it yet. The intergeneration, there are four intergenerational links in this model. Capital formation, so capital passes from one generation to the next after depreciation and investment. Children are educated. Biosphere quality evolves. And finally, knowledge is created. Now, as I said, there are zillions of possible paths which are feasible, given the constraint that we stay within the emission guidelines of the IPCC report, which will stabilize carbon concentration at 450 parts per million. So we don't attempt to do the physical science. We simply take off the shelf the estimates that the IPCC has issued for emission paths now and in the future that will stabilize carbon concentration at that level. And we simply constrain our paths to be ones which will not violate those constraints. Now, what do we maximize? How do we choose a path? Well, let me remind you specifically how we define human welfare. It's a function of consumption of the produced commodity, the stock of knowledge, S is for stock, N is for knowledge, the leisure time of the individual times his level of education, S for skill. And finally, this is the biosphere quality. S bar is something like 800 parts per million of carbon concentration, and this is whatever the current carbon concentration is, 430. So the good stuff is S bar minus the bad stuff. So this is the biosphere quality. Is that clear? We take this to be sort of the capacity of the atmosphere for carrying carbon, after which life would become extinct, or human life. We subtract from that where we currently are, and this is our good stuff left for us. M for model, the bad stuff. We were running out of letters, so we had to resort to French and Spanish and so on. And these coefficients are computed from the data. It's a standard economic problem to estimate what coefficients are in a utility function like this. And the value of these are approximately the following. This is about 0.66. This is about 0.66. They sum up to 1, these four coefficients. This is about 0.3. And the remaining 0.04 is divided between these two coefficients. So we have very small coefficients on knowledge and on the biosphere quality. That's what we get given the current preferences of individuals. You might want them to be larger, but we're not performing an exercise which is saying what we think human welfare should be. We're trying to take human welfare as it appears to be. Maybe in the future, this will rise. People will come to place more value on the quality of the biosphere. But at present, we estimate this to be about 0.01. It's really quite small. So that's the welfare of a generation. And now, in any path we choose, there are going to be subscripts for time on every one of these variables. Okay? So that, and when we have those, that will give us the consumption at day t, the knowledge at day t, the leisure at day t times the education at day t, and the atmospheric quality at day t. So any path is going to be associated with the level of human welfare at every day. Now, among those paths, how do we choose? I will tell you in a moment. I just want to remark upon one rather unconventional thing that we've done. We multiply the leisure of the person by her level of education. So this is educated leisure. That's not traditional in economics. Most economists would not put the level of education there. They would have raw leisure time here. But we say that your life is more valuable if you're more educated. The reason is that you have more choices for what you can do with your leisure time. You can read Goethe if you're educated in German, right? So there are many, so it's a diversity argument. The more educated you are, the more choices you have for how to spend your leisure time. And the more choices you have, ceteris paribus, the higher your welfare will be. So you could attack us for being elitist in saying it's educated leisure time which is valuable to the individual. But I don't think it's elitist, I think it's true. And I think most of us, academics, wouldn't be doing what we're doing if we didn't place a value on being educated for our human welfare. We don't do it just as a way of making a salary. So here's what we do. What we want to maximize, there are two alternatives that we study. The first we call pure sustainability. And that is, we want to choose the path from among all these feasible paths that I've described, which maximizes the level of human welfare that can be sustained forever. In other words, at each date on a path, there's a welfare level, right? Pick the path which has the highest lower bound for all the welfare levels on that path. That's what we call pure sustainability. Okay? So it's a concept of sustainability which is anthropomorphic. It's talking about the sustainability of human welfare. It's not talking about the sustainability of the forests. So green sustainability is a more militant concept that we should actually preserve the natural assets that the Earth has for future generations. That's not what we're doing. We're sustaining human welfare. That will involve a certain amount of sustaining the biosphere quality, but that's not the end all. The end all is sustaining human welfare. So it's sometimes called weak sustainability in the literature. Now, to solve this problem requires specifying precisely what all the economic parameters are. What are the parameters in the production function for commodities and the educational production function, and so on. And we do this using U.S. data, as I said, not due to ethical parochialism, but rather because these data are available and are of high quality. So our computations really have to be interpreted as the sustainability of welfare for the average U.S. citizen. Now, the IPCC report number 4 specifies what the global emissions over time should be to achieve this path which stabilizes at 450 parts per million. The global emissions. But since we are now only looking at the U.S., because of using just U.S. data, we have to decide on how to allocate these global emissions to the U.S. to carry out our computation. So we have to constrain U.S. production not to exceed certain emission levels, right? So we have to get those emission levels from the global emission levels. And we have two scenarios which we compute to do that. The first scenario assumes that the U.S. continues to emit 24% of all global emissions. That's a very optimistic scenario from the point of view of the Americans, right? And the second scenario is a pessimistic scenario for the Americans, that the U.S. emits its per capita share of all global emissions, which is 4%, about 4%. Okay, and we're going to compute the solution to the problem I stated with respect to both of these scenarios. And here are the answers. So this is pure sustainability under scenario 1. Namely, the U.S. continues to emit 24% of global emissions. Now, these are going to be the global emissions specified by the IPCC recommendation. And here's the answer. We get that we stabilize. This is the level of human welfare at date T divided the level of human welfare at year 2000, the benchmark, the beginning. We stabilize at a level of welfare which is about 26% higher than our current level of welfare. So actually welfare goes up. And then we stay here forever. This is pure sustainability. What happens in the pure sustainability model, I said we want to maximize the lower bound for all welfare levels across time. It turns out that we actually equalize welfare levels for all time. There's no growth in welfare in the solution to this program. Consumption actually goes up. It was 27 in 2000. I don't remember what these units are, probably thousands of dollars in some, in 2000 year dollars or something. It goes up for about 1/9. Investment also goes up. It actually takes a big jump at the first date, and then it stabilizes at about 30% higher than it was in 2000. As a consequence, capital stock doubles. And and then it stays double what it is now forever. Knowledge, this is the interesting one. Knowledge goes up by almost a factor of 4. We invest a lot more in knowledge than we're investing now. In the second scenario, this is the pessimistic one for the U.S., that the U.S. just gets to emit its per capita share of world emissions. Welfare still goes up, but only by 16%. So even then, our welfare level increases. Consumption now falls. Consumption is lower than it is. But welfare goes up because the other things that go into welfare increase. Knowledge and education and the quality of advisory. Quality of advisory doesn't increase from 2000, it goes down, but it stabilizes. What happens to these other things? Well, as I said, knowledge goes up again, a huge amount, a factor of 3.5. So we have knowledge and we have education. Education, where's education? We'll see that on the next slide. So this is an interesting scenario because this is the one scenario that looks like what a lot of the green movement says, that we have to reduce consumption. Here we actually do reduce consumption, but human welfare goes up. So this scenario shows the importance of recognizing the existence of other arguments than commodity consumption in human welfare, because it shows we can substitute away from consumption and still increase welfare above the benchmark if we have to. Now, we also compute, this is the labor allocation. So what happens under scenario 1, this is the total value of the, put it this way, it's the level of education or level of skill of the adult at date T. It goes up from 1.4 to 1.85. So people become more educated. And that's one of the reasons that welfare goes up even in that last scenario. Because remember, educated leisure is an argument of utility function. So the level of education goes up substantially. I now want to look at the way education is divided. These are the percentages. These are more informative, probably, into the 4 uses of education. This is, all the X variables are labor. So this is labor, educated labor in educating children, educated labor in making commodities, educated labor in producing knowledge, and educated labor taken as leisure. So what happens is we actually reduce, this was a surprise to us, we reduce the fraction of the labor force that's involved in education from 3.3% of the labor force at the benchmark to 2.8%. However, people are becoming more highly educated because the quality of teachers has gone up. That's what this is telling us. The quality has gone up. The fraction of the labor force in commodity production is almost the same as it is in the year 2000. It goes from 28% to 27.8%. This is the interesting one. The fraction of labor in the knowledge industry more than doubles. So we have more artists, more writers, more researchers, more college professors doing research, more people doing research in corporate labs. And leisure time actually falls. We consume, here we're consuming 2/3 of our time in leisure. Here it's slightly less than 2/3. In the second scenario, that is the one where the more pessimistic scenario, things still go up. In fact, we invest even more in education. Here, the stable level of education, of the quality of the individual's education is 1.858. Here it goes up to 1.884. This is partly a consequence of the fact that we're reducing consumption. So we're substituting more education for consumption. The fractions are very similar to here. In fact, they appear to be identical to 4 decimal places, how the labor is allocated into the 4 uses. Okay, that's pure sustainability. Now the next exercise we conduct is the following. You might say pure sustainability is a rather pessimistic prospect for the human race, that we just have stable welfare forever. So we compute what would be the path that would maximize the welfare of the first generation and then guarantee a growth rate in welfare of 1% per annum after that. 1% per annum turns out to be 28% per generation. 25 years in a generation in our model. So let me say it again what the problem is. Among all the feasible paths, find the path that maximizes the level of welfare of the first generation, subject to the requirement that welfare grow by at least 28% per generation thereafter. Well, why not do that instead of the first path? What's the trade-off between that path and the first path? I mean, everybody wants growth. So there's got to be some trade-off. Well, the trade-off is what happens to the welfare of the first generation. The first generation's welfare is going to be lower in the solution to this problem than it was in the pure sustainability problem. The first generation is going to have to sacrifice to enable more growth. Maybe even the second generation, we'll see. In general, the higher the growth rate we want to sustain, the more the sacrifices will have to be made by the early generations. So here's the answer, again, under both scenarios. Well, it turns out, here's what happens to welfare. It's 1 in the base year. It goes up still 1.2476 in generation 1. And then it keeps going up 28% a year. These are going to go up forever. If you remember what this was in this scenario in the pure sustainability problem, it was 1.25 something. And then it kept on being 1.25. So only the first generation suffers on this path compared to the pure sustainability path, and it doesn't suffer much. Its welfare goes down by less than 1%. So it appears to us that the trade-off is acceptable. I don't have an ethical theory to justify that view, but it seems to us that a relatively small sacrifice by generation 1 can enable future growth at a quite substantial rate. What happens to the allocation along that path? Consumption keeps growing and growing. Investment keeps growing and growing. Capital stock keeps growing. Knowledge shoots way up. Let's look at the second scenario. Again, even in this more pessimistic scenario for the U.S., consumption, well, utility is 16% higher than at the 2000, and that compares. Again, it's a little less than it was here. Here it was 1 point. This is the pure sustainability, 1.1687. So now it's going down to 1.1588. Again, it seems to be a rather small sacrifice by the first generation in order to permit future growth forever. Let's look at the labor allocation. Let's just look at scenario 1. Now we're devoting more time to teaching. We're devoting 3.6% of the labor force to teaching compared to 3.3%. Remember, before we were devoting a little less time. And now look at what's happening to the quality of labor. It's really shooting up. So these people are 3 times as well educated as year 2000 people. And we're devoting more time to teaching. Interestingly, consumption, labor force and consumption stays about the same as it was on the other path. Knowledge stays about the same. Labor force and knowledge, it more than doubles. And leisure goes down even further. Leisure goes down to 64.7%. So strangely, we don't end up taking more leisure, even though we're having a lot of technological progress, because knowledge is going way up. And finally, we do a 2% growth path. 2% per annum is equivalent to 64% welfare per generation. This is about the path the U.S. is on. We have about 2% growth of income, not of welfare necessarily, but of income. So here, again, the first generation suffers. This is compared to 1.25 with pure sustainability, but they don't suffer that much. And the trade-off for their suffering is very rapid growth in welfare. What happens to consumption? Again, it just shoots way up. Capital stock shoots way up. Knowledge shoots way up. What happens to the allocation of labor? I'm just going to skip the second scenario. The allocation of labor, now we're spending 4.6% of our labor force in teaching the young. This stays about the same. This never seems to change. This is the fraction of the labor force in manufacturing. Again, the knowledge doesn't change much from the first scenario, from the pure sustainability. It goes up a little bit, the labor force and knowledge. Leisure goes down again to 63%. I want to say again, all these paths are feasible given that we live within the constraints of the IPCC. And I've given you the two scenarios for how we could look at what the U.S. share is. If we take the second as the lower bound, I mean, this is what would happen if the U.S. gets only its per capita share of global emissions. We still do, you know, we can have welfare higher than we have today and live within those constraints. I say that it's the lower bound on welfare for the U.S. getting its per capita share of emissions for the following reason. Suppose we had the distribution of rights to emissions to nations, which were in proportion to the population. The U.S. would surely buy emission permits through cap and trade from other countries who would want to sell them. So we would end up with more than our per capita share of emissions. Of course, we'd have to subtract from that what we're paying other countries from our GNP to get those rights, which is not done here. Here we're just assuming that we emit our per capita share of the world emissions. So here's the trade-off between growth and welfare of the first generation. Again, let's look at the more pessimistic scenario. In pure sustainability, the first generation has a welfare level 17% higher than the 2,000-year benchmark. At a growth of 28% per generation of welfare, it falls to 15.9% higher. And at a growth rate of 64% per generation, it falls to 14.6% higher. So the sacrifice in welfare for growth is 0.85% for 1% growth per annum of the first generation, and 1.93% for if we have faster growth. Now, some people would say there's no justification for growth. Why should our one generation be worse off than another? I mean, if you take the view that the generation you're born in is a morally arbitrary fact, why should you be worse off than others just because you're born earlier in history? Well, if you take that view, then you should advocate pure sustainability. But we don't necessarily advocate pure sustainability. I said necessarily. Could be convinced, maybe. Because we say that it might be a public good. Maybe human society would like their descendants to be better off than they are. Maybe they're willing to sacrifice something so that growth of human welfare can occur. And if that's the case, then that's a justification. Now, I think there's a limit to how much people in the current generation should have to sacrifice to permit growth in the future. So I'm not sure how much higher than 2% per annum I'd be willing to go. Okay, so the summary is that we can sustain the quality of life at levels noticeably higher than the 2,000-year reference level. There's a small trade-off between the quality of life of the first generation and moderate growth rates thereafter. The most important change required by the implementation of these desirable paths is the more than doubling of the reference fraction of labor devoted to the creation of knowledge. Whereas the fractions of labor allocated to consumption and leisure are similar to those of the 2000 reference level. As I said, they fall slightly for leisure, but it's a slight fall. higher growth rates require substantial increases in the labor force devoted to education as well, on the order of a 30% increase for each additional 1% increase in annual growth, together with moderate increases in the fractions of labor devoted to knowledge and investment in physical capital. Only in one scenario, scenario 2 with zero growth, is there a decrease in consumption compared to 2000. Although welfare remains greater than the reference year, and this one case, this might be the case that the Green Movement has emphasized, shows the importance of modeling welfare as comprising more than simply consumption of commodities, because welfare can go up even though consumption goes down. Okay, I now want to say some words about the second problem, international equity at the current generation. So the elephant in the room today is how to share the responsibility for cutting back emissions among nations. The U.S. and China, as I said, each emit approximately 1/4 of global emissions. An agreement between them is necessary and I think sufficient to enable an international global agreement. In other words, if the U.S. and China succeed in hashing out how to do it, I think everybody else will fall into line. So how should China and the U.S., think the global north and the global south, if you will, share the emissions quotas of the IPCC? The Copenhagen conference, unfortunately, was essentially a failure. There was no international agreement of any content. On the final day, a so-called agreement to limit emissions to generate no more than 2 degrees Celsius increase in global temperature was made, but there were among 4 or 5 countries, but there were no details and no plans and no enforcement mechanism. Hopefully these details will come forth soon, and I think the failure, my own view, is that the failure in having better in the Copenhagen conference was due to the fact that the Obama administration was so totally tied up in the healthcare legislation this year that it didn't spend any time on climate change. And so it had nothing really to propose in Copenhagen. I think everybody was waiting for the U.S. to take the lead. So, what should the principle be for how to share these emissions among countries? Now, I have to say this part of the talk is more tentative than the first part. There are all kinds of ideas floating out there. One is that the North is responsible for the present level of carbon concentration, and so they should bear the brunt of having the cutbacks, and the South should therefore have the lion's share of the permits. Another kind of egalitarian proposal is to allocate permits to countries on the basis of population. I just want to note that cap and trade, which is talked about a lot, is not a solution to this problem. It doesn't tell us how to make the initial endowments of emission rights to countries. Cap and trade tells us how to readjust, how to find an efficient allocation of the emission rights after the initial endowments have been made to countries. But it doesn't tell us how to make the initial endowments. You can't do those by cap and trade. I mean, who would sell these international emission rights to different countries if you wanted to have an auction? The UN? And what does the UN do with the income? Just how does it distribute it to countries? So there's no way of making the initial allocation of emission rights to countries through cap and trade or an auction. That has to be solved somehow, that problem. And then cap and trade is like a market. After the initial endowments have been made, the market will reallocate the rights in a way that, in which people are paying something which makes it, which they're willing to pay. So, I want to make a proposal for what the fair way to allocate these rights. Not the fair way, necessarily, what a politically feasible way is to make this initial allocation of rights. And let's simplify the problem by just thinking of the U.S. and China. Suppose we could agree that if there were no climate change issue, we didn't have to worry about greenhouse gases, that Chinese GNP per capita would converge to U.S. GNP per capita in N years, maybe N is 75. I'll show you a calculation in a minute suggesting why n might be about 75. I would propose that with the emissions constraint that we have, the IPCC constraint, we should distribute the emission rights so that we still converge in n years. In other words, that the year of convergence remain the same. Now, I would argue this is a politically feasible proposal. The difficulty in this proposal is going to be agreeing what n is. But let's put that aside for a moment. Let's suppose we can get together an international commission of Chinese and American economists, and they agree what n is, what the year of convergence would be, absent the problem. And here's why I think it's a negotiating equilibrium. Well, so China and the U.S. are sitting at this little circular table for negotiations. You know why they have to have circular tables in negotiations. Anyway, suppose China makes a proposal in which they converge in less than n years, fewer than n years. Well, in the UN, the U.S. can say, why should you benefit by virtue of the global warming crisis that we're facing? Why should you converge earlier than you would have otherwise? And likewise, if the U.S. were to make a proposal saying that we should converge later than 75 years, China will say, why should you benefit by virtue of this crisis? So that says the only equilibrium in the negotiations is that we agree to converge still in n years. Then neither can claim that the other side is benefiting. Now, this is assuming that there's an ethical focal point, which is the year of convergence. That's the assumption behind this argument. I may be wrong that that's an ethical focal point, but it seems to me it is a possible ethical focal point. That it's the year of convergence which measures, the length of time it's going to take China to catch up, which is the focal point. Well, here's a quick calculation. U.S. GDP per capita, 2008, was about 47.4 thousand. Chinese GDP per capita was 5.97 thousand. 1 plus the U.S. growth rate was 1.02. 1 plus the Chinese growth rate, actually China's been growing about 9%, but let's say that they reach the technological frontier fairly soon and their growth rate drops to a mediocre 5% per year. Let's call that 5%. Then in T years, China's GNP will be 1 plus their growth rate to the power T times their present GNP. And our GNP in T years will be 1 plus our growth rate times the US GNP. So we'd like to solve this equation. When is the ratio of these equal to 1? That's the year of catch-up. If you solve this equation, you get T equals 71.5 years. So there's a back-of-the-envelope calculation for why I say 3 generations. So what we're doing now is the following. We're building a model in which we have 2 households at each generation. A Chinese household and an American household. Each household has an adult and a child. Otherwise, it's the same model as I've shown you, except they're 2 households. And what we want to do is calculate the optimal path, given that we stay within the constraints of the IPCC on emissions, on global emissions, given that we stay within those constraints, which will entail Chinese convergence to the U.S. in welfare, not GNP per capita, but in welfare in 3 generations. And then after that, they just grow and sink forever at, let's say, 2% per annum. I mean, we can pick the growth rate we want. We're going to solve that problem. We haven't yet solved it. We're going to solve that problem. And that will, part of the output of that problem will be how the emissions should be allocated between the U.S. and China. That's going to be one of the variables in the problem. So we're only taking the constraint is that global emissions should be IPCC, but how they should be allocated between China and the U.S. is part of the optimization. So this will give us a recommendation for how to allocate emissions between the U.S. and China. Quite a different approach from the idea of per capita, equal emission rights. It's based upon this idea of the bargaining focal point. So the general rule is that emission rights should be allocated so that the growth factors of the two countries remain equal. The growth factor is 1 plus the growth rate, not the growth rate. Remember, it's 1 plus G that you multiply times GNP to get GNP at the next year. So in particular, if we both have to cut back on our growth factors, there will be some common factor, D, by which we have to multiply both our growth factors. D will be some number less than 1, but as long as we apply the same D to both of our economies, we will still converge at the same rate. What does that mean in terms of the growth rates? Well, this is the only slightly technical slide. D times 1 plus G is D plus DG, which we could write in this way. So this is the new growth rate. This is the new growth factor, 1 plus something. So the something is the new growth rate. And if we look at the new growth rate divided by the present growth rate, it's equal to this. And you notice the bigger G is, the smaller this is, and hence the bigger this is. So it turns out that the Chinese will have to cut back their growth rate less than the U.S. because they have the bigger growth rate at present to maintain equal growth factors. Anyway, what's the fly in the ointment? I think it's U.S. national politics. Currently, there's a bill in the U.S. Senate to impose emission cutbacks that are not sufficient. They don't get down to 2 tons per capita by 2050. They get down to something like 5 tons per capita by 2050. But even it apparently has no chance of passing. I think it's the ignorance of American citizens, plus the linking by the Republican Party of global warming fears with the left that is making this politically infeasible at the moment. For instance, Sarah Palin, I think, still does not believe in global warming. Now, what does our model recommend as to what the emission rights should be? As I said, we have not yet solved the optimization problem, but we are computing as I speak. The summary is it's perfectly feasible to sustain human welfare at levels higher than today and live within the constraints required to preserve global temperature below 2 degrees Celsius increase. Even less than that is possible. Moderate growth of welfare is probably ethically preferable to pure sustainability because of the small trade-off that I discussed. Reasonable negotiating principle is to cut back the growth factors of all countries which are sufficiently rich by the same percentage. I would have special allowances for poor countries that they don't have to cut back at all until their level of GDP reaches a certain amount. The stumbling block is political, not technological. You seem...
Well, it's just that the entire time you've been talking, that's what I've been thinking, you know, and like everything you've been saying, I've just been thinking, but there's no, because of this lack of political will, none of this really matters, and then it's the fly in the ointment.
We have to make it matter. We have to make it matter. The stumbling block is political. In particular, I think, the stumbling block is here. I don't think it's in China. I think it's here. I think it's the ignorance of the U.S. citizenry abetted by populist propaganda that global warming is a left-wing plot. What do I think is going to happen? I have no prediction. I think the success of Obama in countering the right-wing attack is of utmost importance for the eventual positive resolution of the problem.